Alright, so in this video we're going to be talking about another example. This one is going to be a little bit more complicated than what we have seen so far. So essentially we have a curve that is composed of two curves. So we have C1 here, which is a straight line segment going from point -5, -3 to 0, 2. And then we have C2, which is a curve represented as a function of x as a function of y. So we have a parabola, but it is with respect to the x-axis. And it is also going from those 2 points. Now the integral that we want to evaluate, this is the line integral that we're given in the question. And you notice that the form in which it is represented is different from what we have seen so far, which is just f of x y ds. So instead of having it in this form, we have a broken down kind of form in which we basically have y squared times dx plus x times dy. So it's going to be exactly the same thing. Now the difference is that we're not going to have ds involved in here, so we don't have to take any square roots, but we have to represent y and x in terms of single parameter. And of course, in order to evaluate the whole line integral, we need to evaluate the line integral for each of the curves and then add them together. So for C1, because we have this straight line segment from this point to that point, we're going to use the following parametrization using the vector representation. So we're going to have the initial point and then the final point, and then the limits of integration are going to go from 0 to 1. We could also represent this as a function of x, so y is a function of x, but that would take a little bit more time, so this one is usually more straightforward to do. So what we do is, well, we're going to have two equations, one for x. So what we do is we replace the coordinate. So this is the starting coordinate, that's -5 here. And then the final coordinate on x is going to be 0. So we plug that in and we get this expression for the function of t for x. We do the same for y. So now we're going to have plug in the initial point, which is -3. And then the final point here, rearrange, and then we just get this expression. So now the question is, well, what are going to be dx and dy? Well, we're going to differentiate each of them in terms of t. So we're going to grab this expression, differentiate with respect to t, which is going to be 5. And then basically this is the same as saying dx equals to 5 dt. And then for y, we're going to have dy over dt equals to 5 as well, such that dy is equal to 5 times dt. So now we're going to grab the line integral for the curve C1. We're going to have y squared dx plus x dy. And we're just going to replace in all those values. So same for y and x. So we're going to have integral from 0 to 1. Those are the limits of integration. Y squared, well, we're going to grab this expression here. We're going to square it. 5t minus 3 squared. And then we're going to multiply this by the element dx, which is right here. So it's 5 times dt. And then we're going to do the same. So we're going to grab this expression here. So x is just 5t minus 5. And we're going to multiply it by dy. And dy we just found to be 5 times dt as well. So now all we need to do is rearrange this so that we can integrate with respect to t. So how about we take the 5 out? So let's have 5 times the integral 0, 1. And now at this point, obviously, we need to expand this out. So we're going to get 25t squared minus 15t minus 15t. So that's minus 30t. And then plus 9. And then, of course, we're going to have plus 5t minus 5. All of this with respect to t. So now we have 5 from 0 to 1. Let's see how we can group this together. So we have 25t squared minus 25t. And then we have 9 minus 5, that's 4. So we have this integral here, which is quite straightforward to evaluate. So now how about we go about integrating this? So we're going to have 5 times the integral of this. So this is going to become 25t cubed over 3 minus 25t squared over 2 plus 4t, and then we're going to have 0 to 1. So what is this going to become? Well, we're going to have put 1 into everything, 25 on 3 minus 25 on 2 plus 4, and then we put 0 into everything, so that's just 0, and then in the end we're going to have the following result. We're going to have minus 5 on 6. So this is going to be the line integral for the curve 1. Now we're going to do the same for curve 2. So if we go up here, this is the equation that we're given. So let's write C2 is equal to x equals to 4 minus y squared. And you notice that x is explicitly a function of y in this case, so we can say that y is an independent variable. And then y is actually going to extend between the following limits. So all we need to do is we need to look at this expression, and we need to say, well, it is going from this point to that point, and the limits are along y. So we're going to have minus 3, and then y goes all the way to 2. So we're going to have y going from minus 3 all the way to 2. So this is going to be our parametrization for this particular curve. So now what we need to do is we need to find what the elements dx and dy are in terms of those parameters. So in this case, we're going to have dx over dy. So remember, y is the parameter now, so we're going to differentiate that with respect to the parameter. This becomes minus 2y, such that dx is simply minus 2y times dy. And then for y, we do the same, so we differentiate y with respect to the parameter, which is just itself. So this is just going to be 1. So dy is just going to be dy, which is not unexpected at all. And now we're going to grab the integral and we're going to evaluate it between those limits. So we're going to have line integral of c2 of y squared dx plus x dy. And now we're just going to plug in everything. So we're going to have minus 3 to 2. Here we have y squared. Well, y is just equal to itself, so that's y squared. Now the element dx we just found is minus 2y times dy, so we have to put that in here like that. And then here we're going to have plus this whole expression here, 4 minus y squared. And then times dy, and dy we found is just equal to itself. So now we just need to rearrange this a little bit so we can evaluate it. So we're going to have minus 3, 2. Here we have minus 2y cubed dy plus 4 minus y squared dy. And then we can probably group these things together. So we have minus 3 to 2. Let's see what we have. So we're going to have 4 minus y squared minus 2y cubed dy. So now we just integrate this as we normally would. So this is going to be 4y minus y to the power 3 over 3. And then minus 2y to the power 4 over 4. Evaluated from minus 3 all the way to 2. And now we just plug in those values and see what we get. So for the first substitution, we put 2 in there, we're going to get the following. We're going to get minus 8 over 3 minus the lower bound, so we just put that in here, and that gives us minus 87 on 2 and then if we add these two together we get 245 over 6. So that's our answer for the second curve. And now all we need to do is to evaluate the final line integral is just to add those two results together. So we're going to get the line integral of y squared dx plus x dy is going to be equal to the sum of those two results. So for the first one we got minus 5 on 6. And then for the second line integral we got 245 on 6. And then we get 240 on 6. And this is going to become I believe it's going to be 40. Let me see. Yeah, it should be 40. So that is it. That is the final result we get. So you notice that in this case we had a little bit of a more complicated example, because we had the following functions. We had a line segment going from this point to that point, and obviously it was more convenient to write it in this form. And then for the second one, we had a function of, so we had x as a function of y, so we needed to get around that. But you notice that the procedure is kind of the same, and even when the line integral is given in this form, which is different from that, we can still find dx and dy in terms of a single parameter, so that we can integrate this in the regular way.